It's my pleasure to introduce Tomasz Szarek from Gdańsk University of Technology and IMPAN, who will talk about distortion in the group of circle homeomorphisms.
Okay, so thanks for the invitation. So I'd like to, I'm not familiar with Zoom systems, but I would like to, start in. Okay. Do you see my slides?
Yes.
Yeah.
Okay. Okay, so thanks for inviting me to this seminar. I'm pleased to be here as a speaker again. My talk will be about very elementary things. So I'm very happy because this will be probably my first talk during this seminar, when I will be able to provide the proof with all details, and the lectures will be self-contained and very elementary. So I tested this lecture with high school students, and they understood everything. So I think that is this pleasure to give such talk that the whole audience will understand all details. This is my joint work with Juliusz Banecki. Juliusz Banecki was a high school student when we started working on this problem. So he was a smart guy, a very brilliant student. And when I organized some seminar for the smartest high students in Gdańsk, in our branch of institute, I invited also Julek, and he was interested in dynamical system theory. So we started working on the problem about distortion, and the results of our work will be presented at this seminar now. Okay, let me introduce the main hero of this talk. This will be distortion. So this is the concept taken from geometric group theory. It was introduced by Gromov, who studied some abstract groups and proving the structure or linear structures of this group. He used this concept. And next, it was also used in the theory of dynamical systems. But generally speaking, we assume that we have some group. This is group which is finitely generated. So we have some finite generating set, say G. This is calligraphic G. And we may define on this group the following distance. The distance between two elements of this group is equal to the infimum over all positive integers, such that we may find some finitely many elements, say F1, Fk, from this generating set G, and some constants, epsilon 1, epsilon k. This epsilon y1, epsilon k are either minus or plus 1. And we assume that such constants and such elements, that G2 will be equal to F1 epsilon 1 up to Fk epsilon k G1. Okay, so in the case when G1 is equal to identity, it just this formula just says that G2 could be, this word could be expressed in the alphabet of this generating set G by k elements. So F1, Fk are either these generators of this group or inverses to this generator. So because epsilon is either plus or minus 1. Okay, so it says just something about the length of the minimum of the length of the word expressed in the alphabet of this generating set, calligraphic G. If H is an arbitrary group, because we assume that G is finitely generating, but now we can assume that H is an arbitrary group, and an element, say F from this group, will be called distorted in H if there exists a finitely generated subgroup G. This is, sorry, a finitely generated subgroup G, F is in this subgroup, such that the length of the iterates of this element F grows sublinearly in N. So the distance, equivalently, the distance between Fn and the identity. So this distance is just how many elements in the composition from some generated set we must have. This will grow sublinearly in N. It holds for some generating set, but it's easy to see that it is independent. This limit is equal to 0, so it is equal to 0 for all generating sets. Because the distance, if we take another generating set, so we have two generating sets, so we know that the distance in one of these generating sets is bounded from above by some constant times the distance in this represent each generate on this new generating set, but elements from the previous generating set. So that's extremely simple. Okay, now look that the limit always exists. Why? Because if we take this term in the numerator of this expression, so we see that it is a subadditive. This is subadditive sequence. So this subadditive sequence divided by n will have limit. And we are interested in the question when this growth of this distance divided by n tends to 0. As I said, this notion introduced Gromov. It was in 1970s, but in 1990s it was used in the theory of dynamical systems. In particular, there's a nice paper by Calegari and Friedman, who in 2006 proved that each homeomorphism is distorted in the group of sphere homeomorphism. This is a very nice result, but with very intrinsic, complicated proof. They used some Kirby-Zieberman theory about factorization in the group of sphere homeomorphism. There's also a question asked in the paper whether it's possible to provide a simple proof in the case of this general sphere homeomorphism. It is still an open question. They proved also that rotations on the circle are distorted in the group of C1 diffeomorphisms, and asked several questions about distortion in other groups of homeomorphism. In turn, Artur Avila proved, they asked several questions, and among others, this question about the distortion in the group of smooth diffeomorphism. It was answered by It is again not too long paper. However, the proof is not. It's again it's very difficult, and he uses Hermann Yoko's theory on smooth conjugacy and other advanced tools. But generally speaking, the idea, there's a nice geometric idea behind this proof of Avila. Namely, he defined a homeomorphism on diffeomorphism on the interval, such that and divide this interval into countably many subintervals, disjoint subintervals, and on each of this interval, he, in some sense, a very clever way, was able to code the subsequent iterates of this homomorphism, distortion of which he was looking for, and in some sense, having this and defining this homeomorphism, he was able to decode from this one homomorphism using some results on very advanced results from the theory of conjugacy of such homomorphism or diffeomorphism, and prove that all rotations are distorted. Okay, at the same time, John Franks, Michael Handel, and many others asked about distorted rotations or about distorted rotations in the group in other groups. In particular, it was asked whether irrational rotations, because the case of rational rotation is very simple. If it is periodic point, so it is of course distorted element and distorted element. But it was asked whether irrational rotations are distorted in the group of piecewise-affine circle homeomorphism. In particular, Andres Navas at his talk at last International Congress of Mathematicians 2018 provided the list of open questions concerning the dynamics of the circle. And he asked the question about the existence. So he asked whether it exists a distorted irrational rotation on the circle, which is in the group of piecewise-affine circle homeomorphism. It is impossible to extend this result by Avila because, as I said, he defined homomorphism which was composed of infinitely many homomorphisms. So this piecewise-affine property may not be preserved in this construction. Well, the purpose of my talk is to give answer to this question, and from now on we will assume that our group is either the group of piecewise-affine circle homeomorphism or smooth diffeomorphism. So G could be one of this group, but you will see that the construction is so general that we will be able to extend to other groups of homomorphism because we will have some freedom in defining this. And what is the purpose? The purpose of my talk is to give the proof of this theorem I wrote here, namely that all irrational rotations are distorted in G. Either the group of piecewise-affine circle homeomorphism, and this is a new proof. And in the case when this is our smooth homomorphism, this gives an elementary and constructive proof obtained by Avila and his paper. So, as I said, the proof will be extremely elementary. So, I don't know how to, sorry, I don't. The proof will be elementary, so I will be able to provide all details. Okay, let us define some subgroup of elements. G-truth. What's G-truth? G-truth is the family of all homeomorphisms which are trivial on some set. So if G belongs to G-truth, it means that there exists some non-empty open set such that this homomorphism is invariant. So this is such homomorphism that on some sub-interval, it is just equal to identity. Okay, so it could be something like that. Yeah, it doesn't matter where this interval is located. There exists an open set that this homomorphism is equal to identity on this open set. And now we will also introduce the family of all rotations. Will denote it by capital T. T alpha, this will be rotation with rotation number alpha. And I would like to prove this theorem that all irrational rotations are distorted in G. Okay. The proof, before we give the proof of this theorem, which will be extremely simple, if we have the following two lemmas. So we first formulate two lemmas, and we will deduce the theorem from these lemmas. And in the second part of my talk, I would like to give the proofs of these lemmas as well. So they will be elementary. Everything will be elementary. So what we have in lemma 1? In lemma 1, we have the following situation. So we have this in our irrational rotation, and we take an arbitrary function which is either G-truth or rotation. And then there exists a finite generating set GG in this group G. We remember that G is either the group of piecewise-affine homeomorphism or smooth diffeomorphism. So there exists a finite generating set G and some constant, positive constant C, such that the distance of T and alpha, G, T and alpha inverse, the distance between this element and the identity is less than C times log n, and it holds for all n greater than 1. Look at this lemma. It is obvious in the case when G is a rotation. When G is a rotation, so since these elements commute, so we get that this is equal to G. Yeah, this is equal to G. So this is obvious if G is a rotation. If G is trivial homeomorphism, the situation is a bit more difficult, but not too much. So I hope that this will be easy to access, and I will give the proof soon. But before we do this, let us formulate the second lemma. The second lemma, which is a bit tricky, but it took some time, we formulated and proved this proof. But it is also elementary. So in what Lemma 2 says. Lemma 2 says that in G, we are able to find some elements, G1, GL, which belong to this G3 or our rotations, and some integers, K, K1 up to KL, such that K is different than K1 plus K2 plus KL. And for each sufficiently small beta greater than 0, if we take this rotation with rotation number beta, it will satisfy this identity. X to the power K1, G1, X to the power K2, G2, and so on, X to the power KL, GL is equal to X to the power K. So this identity holds for all T beta if beta is sufficiently small. This is the lemma. This is lemma 2. So I think that the most difficult part of this proof was just to find such identity which will be satisfied by all rotations with beta sufficiently small, and which will satisfy this condition K. So the power on the right-hand side is different than the sum of the powers of X on the left-hand side of this identity. Well, so we can go to the proofs, but as I said, first I'd like to give the proof of the main theorem, so to deduce the theorem from these two lemmas. Okay, so fix an irrational rotation T alpha. From what we know, from lemma 2, we know that in G, there exists an equation. I will write down this equation here. This will be the equation, as you remember, it was equation xk1 g1 xk2 g2 xkl gl is equal to x to the power k. And this equation is satisfied for all T beta if beta is sufficiently small. So for all rotations with sufficiently small rotation number beta. So x equal to T beta will satisfy this equation. Now, from lemma 1, what we know from lemma now? From lemma now, we know that there exists a generating set. Okay, so we should keep in mind that these elements GL are in G3 or are just rotations. And we know that there exists some generating set JL such that what we know that T alpha to the power n GL T alpha to the power n, this distance between identity is less than some C log n. And it holds for all G1, G2 up to GL. So we take a generating set, which will be again finite generating set G. And we know that in this, for this generating set, we have this bounds on iterates of rotations with rotation number alpha. But we may rewrite equation 1, and now will be easy to see why we're looking for such equation, for the equation of this type. We rewrite this equation in the new form. So we want to have here a conjugacy of subsequent elements. So we have x to the power k1, g1, x to the power minus k1. Here we will have x to the power k2 plus x to the power k1, because we had here x to the power k2. We want to have conjugacy, so this will be x to the power minus k2 minus k1, and so on and so forth. So here we get x to the power k1 plus x to the power gl. And since we want to have this conjugacy, so we put here x to the power minus k1 minus kl. So on the right-hand side, we'll have to add the same term. So we will have k minus k1 minus kl. And the crucial thing is that we assume that k is different than k1 plus k2 plus kl. So this is non-zero. This power is non-zero. And we said that k minus k1 minus kl is equal. We put that this is m. And we know that for sufficiently small beta, so for beta less than, say, beta 0, x equal to t beta will satisfy this equation. Okay, but what we are doing now, we take an increasing sequence ni, such that if we take ni times alpha, they will be in the interval 0, beta 0. So they will be modulo 1, of course, they will be less than beta 0. It is possible because we remember that alpha is an irrational number. And from lemma 1, we know that that we have this bound. So T alpha and A and I times K1 plus Kj, Gj, and the inverse of this term, the distance is less than or equal to some constant time log ni. Yeah, it was proved. So it is proved in lemma 1. Okay, if we know this, we see that firstly, we can put x is equal to t n I alpha, because n I alpha was between 0 and beta 0. Therefore, if we take this will be the right hand side. Yeah, this will be just t alpha ni k m, just m. So we know that the length of this word is less than the length of all these words. We have bounds on these words in the alphabet G, calligraphic G, because it was equal to the union of all these alphabets for all these elements. So this is again finite set and a nice generating set. But so we see that the length of this is less than or equal to the sum of all these lengths. So it is written here. It is less than the sum from j equals 1 to L, C j times log ni. But this is bounded from above by some constant C log ni. And now we see that this growth is sublinear, so the limit, because as we said that this limit always exists, so we may go to some subsequence. So we take this for the subsequence Tnim. So this divided by Nim will be less than some constant C over N times this limit, log Ni over Ni, but this is equal to 0. So the proof of this theorem is complete. So as we know, as we see that having these two lemmas, the proof is elementary. So, but as you may suspect, so the key ingredient of this proof is the proof are the proofs or these two lemmas. So let us start with the proof of lemma 1. Before I do this, because there are some technicalities, it's a bit technical, but I would like to sketch the idea which is behind this proof, which is a very elementary idea. Namely, if we have some rotation T alpha, and if we take the following composition, T alpha, H inverse, where H is equal to X over 2, half of X. What we obtain, of course, the problem is that this is not, this is not a homeomorphism. Yeah, this is not homeomorphism, but we'll try to do this to make of it a homeomorphism. What is the result of this composition on some point X is equal to, so first composition will be X half plus alpha, and we take this multiplied by 2, so this will be X plus 2 alpha. So this will be 2 alpha. So, and then the same, in this way, if we take the distance of 2t, say 2 alpha, this will be less than or equal to the distance of T alpha identity, plus we took here two elements, H and H minus 1, so plus 2. And it holds for all N alpha. So it will be that to N alpha identity, this will be the same T N alpha identity plus 2. So we see that the growth of the length of this word T to the power T or to the power 2n alpha or rotation with rotation number twice n alpha will be less than rotation of Tn alpha plus some constant 2 in this case. So we see that in this case the growth is bounded from above by some log n. So this is the idea. However, we can't use this idea because this is not homomorphism. And we can't, we go beyond our group. But if we restrict to some subsequence, we will be able to take some homomorphism which will act in similar way. So now take an interval. So what we are going to do now, we'd like to prove. would like to prove that the length of this T and alpha H or G T, here is alpha, here is N, T alpha minus N, that this will be, the length of this will be less than some log over N. But G is either G-triv or rotation. We notice that there is nothing to do where when G is a rotation, because it commutes, this formula, these elements commute. So it is obvious, but we assume that G is an element from our family G-triv. Okay, so therefore, G is equal to identity on some subinterval of interval 0, 0, 1. Well, we see this easy observation that we may assume that our interval is equal to A to 1. This is here. Okay, this is from A to 1. Why? Because if it is not this interval, so we can transform this interval onto this interval or into this onto this interval, on this interval, or shift this interval using some rotation. If we use some rotation, so this rotation we put here will commute and can be moved out. So this is easy to observe that we can assume that this interval is just from A to 1. It is just for simplicity. So our computation will be much simpler if we assume that this is this interval. And what we are going to do, we will prove that we are able to define some homeomorphism Hn, which will be equal to T alpha n on this interval 0, 1, excluding our interval I. So this will be such homomorphism that it will behave like our rotation, but this will be only on all elements from 0, 1, excluding elements from this interval I. If we will have this is the main part of this proof. If we have this, we will be able to obtain our theorem quite easily. So I will show this a bit later. But now we focus on doing this. As I said, we can assume that that this interval is interval A to 1. We take some constant m, which is some integer bigger than 1, and we assume that m is sufficiently large, so a plus 2 over m is less than 1. And now we take this homomorphism, you know already, namely we take h from G such that h of x is x half for all x on the interval from 0 to a plus 2 over m. So we have here some 1 over m. We know that a plus 1 over m, this is less than 1. And we take homomorphism, which is just half, 1/2 of x, so x over 2. We don't care how this homeomorphism looks outside this interval. So you see we have some huge freedom here. We can make it piecewise-affine, or we can make it smooth. How this homomorphism is defined beyond this interval from 0 to a plus 2 over m. And we take some rotation Rx, which is equal to x plus 1 over m. So what we obtain? Now we define the sequence Hn of this homeomorphism by induction. So H0 will be identity. If n is odd, we just put Hn T alpha Hn minus 1. So we see that H1 is equal to T alpha. Okay? Now, if n is even, we may define the following homomorphism, namely composition of H and half and H. And what is and observe how this homomorphism behaves on the interval from 0 to A. Well, h of x, we remember it is 1/2. Hn, so if we take from 0a, this interval is transforms on 0 to 8/2. On this interval, Hn half behaves like a T n alpha, n half, alpha to the power n half. So if we take T alpha n half, so we obtain that this is n alpha over 2 up to 8/2 plus n alpha over 2. Okay, but now we can take, remember that we took also we took also rotation R, which was equal to x plus 1 over m. So now we can take some k from the integral from the set 1 to m, such that n alpha half, so this beginning, plus km will be in the interval 0, 1 over m. We shift this using using this r to the power k. So k times using this shift, we moved this to the interval from 0 to 1 over m. And therefore, if we take rk on this will be transformed as r to the power k on this will be to 0 a/2 plus 1 over m. So this will be again in the domain where h was 1/2. No, not exact. No. To h was, yeah, h was 1/2. Yeah, h was 1/2. Therefore, if we take the inverse to h, this will be twice this. So we obtain, I don't know how to switch off this. Okay, so if we take this and we take h inverse to this, so the formula for h inverse is 2x because it was x half. It was on the interval a2 plus 1 over n, but on the interval a plus 1 over n, the formula was for hx was 1/2. And therefore, the inverse of this is just 2x. So we obtain that this is, if we take this composition, we obtain that this is x plus an alpha plus 2k over n. And now, if we take act 2k times with the inverse to this rotation with rotational number 1 over m, hn will be equal to t alpha n of x. Yeah, because this is 2k times minus 2k over m. So this will be t alpha n of x. So this will be the condition we wanted to obtain. So that on the interval, because you see it was done on the interval 0a. It was on this interval. It was on 0a. Yeah, everything, all computations were done on 0 on the interval from 0 to a, and if we define that this is hn, so we see that hn of x is equal. Oh, this is hn. Sorry, this is hn. We see that hn is equal to t alpha n of x on the interval from 0 to a. So now we can take this generating set t alpha hr. This is our generating set. So it consists of only 3 elements. And we can see now that the length of hm is less than or equal to, now look at hn is even. So the length of hn is equal to, of this word, is less than or equal to hn². So this is this term, plus h inverse. So there's our 2 plus 2k. So this will be 2k plus 2. No, 3k, yeah, because it's here. So it is k times this, 2k times this. So this is 3k plus 2. But k is less than or equal to m. So this is less than 3m plus 2 plus this term. I put here 3 because in the case when hn is not even, it is, if it is odd, so we know that hn is equal to t alpha hn minus 1, and we have to add one term, one homomorphism in this composition. So we have to add 1 to this, and in this way we obtain the following recursive inequality. So hn is bounded from above by some constant. You see this constant depends on the interval only, and the length of hn². So from this, it follows that we may estimate this element by some constant c times log n. Okay, so what we know? We know that t alpha to the power n is equal to hn, but it is done on x 0, or if x is not in I. However, we see that this formula is satisfied. Why this formula is satisfied? Because if hn, if we take here some set from n alpha, a plus n alpha, and we take x from this set, and so we see that hn g hn inverse will be the same as t alpha n g t alpha minus n. Why? Because t alpha and hn were equal. They were equal on for x 0a. So on this set, they are equal. But these are homomorphisms. Both are homomorphisms. So hn is homomorphism. And also, and if we take x, which is not in this set, is not in this set. So hn inverse of any element x will be in the set a to 1, because it was homomorphism. If it is in this set, we obtain here that this function g is identity over there. So this formula is equal to hn identity, hn inverse identity hn. So this is just identity. And the same holds here. So because these functions were not equal on the whole domain, but having this, we obtain that this composition is equal everywhere. Because if we take the inverse here, we enter into the set where this function is g, and the function g is equal to identity, and it cancels. So this will be identity as well. Therefore, we have that this equality. If we have this equality, so we know that the length of this word is the length of this word, the length of this word, and the length of g, but hn was bounded from above by c log n. So we obtain that in this t alpha n g t alpha inverse identity is less than or equal to some new constant c log n, and we are done. So the proof is done. So as you see, it's elementary, completely elementary. So just okay. So now I can go to the proof of lemma 2, which is again very simple but a bit tricky. So it took some substantial amount of time to prove this result. But if you see, you will see that when we can write this, it's very obvious. Well, now we take some constant, I don't know, beta. But beta, what we have to prove? We are looking for the equation of the form x to the power k1, g1, x to the power k2, g2, and so on, x to the power kl, gl, and it is equal to x to the power k, and we will have to have that k is different than k1 plus kl. This is this is our lemma 2. Okay, so take beta, sufficiently small. So for our consideration, beta less than or equal to 10 to the power minus 3 will be sufficient. And we take the function, so f function, f1 from g3. So we remember this is our functions which are which are equal to identity on some interval, subinterval of 0, 1. And this function is defined in the following way. On the interval from 0.4 to 0.6, it is 0.4 plus 2x minus 0.4. And this is equal to x from 0.9 to 1 and from 0 to 0.1. So let us draw this function. How this function looks. Here we have diagonal, and this function on some small set, let us use, on some small set is equal to identity. And here we have 0, 4. This is something like this. This is, of course, homeomorphism because twice value for 0.6. So this will be here, probably something here. So the value, okay. We have this function. We can extend again this function to obtain a function from the group G. So piecewise-affine if we want, or smooth diffeomorphism. It is up to us what we want to obtain. And having this function, we have this function. We take the following composition: the inverse of f, 2 beta, f1, and inverse of 2 beta. And now what we have, it is again obvious that if we take from x from the interval 0.41, 0.79, then hx will be x plus 2 beta. Why it is so? What's going on here? So we take x from 0.41 and 79. So f inverse, this will be, what's the f1 inverse? F1 inverse of x is the same, yeah? This is 1/2 and x minus 0.4 plus 0.4, yeah? If we take this, so we see that on this interval from 0.41 to 79, this will be this formula for the inverse. So this will be this formula for the inverse. So we take 2 beta, composition with 2 beta. So this will be plus 2 beta. And now we take f1, but having this, we will be in the domain where f1 is equal to f1 is here. This will be if we are from 0.4, 0.6, so we see that this will be something like that. So what is the formula for this? The formula for this is this formula. This formula, because we are transformed to this interval, from this interval, we are transformed to this interval or to some sub-interval of this. We take 2 beta, so we shift slightly this, but it doesn't matter. We will be again in this interval. So if we are in this interval, so if we take f1 of this, this will be twice this. And if we take minus 2 beta, this will be minus 2 beta. So we see that this will be 4 beta and minus 2 beta, so will be 2 beta, and the rest will cancel. So we get that this is x minus 2 beta on this x plus 2 beta, yeah, because 4 beta, yeah, because will be 4 beta minus 2 beta, so will be x plus 2 beta. So this is x plus 2 beta on this interval. And again, h1 of x is x4 on this interval. From here was 0.9. Here we'll take a smaller interval to assure that if we take this translation, we will be still in this interval because we take translation to beta, but 2 beta is sufficiently
Do you have connection?
I can't hear Tomasz. Did we lose him? Tomasz, are you here?
Not on the list of participants either, so he lost connection.
I cannot hear him too.
Let's wait a bit.
I will call him, but probably he understands that he lost connection.
But he's in the list of participants now.
Yes, now he is back.
Ah, here.
Okay.
But we still don't hear him.
Tomasz, we don't hear you if you are here. Alex, do you have his number?
Yes,
Maybe it makes sense to call him.
I will call. 1 moment, I will take my phone. I found my phone. I'm calling. Straciliśmy kontakt z tobą z 2-3 minuty temu. Nie słyszymy cię. Jesteś tutaj w liście uczestników, ale nie słyszymy ciebie. Dobra, cześć. He will try to do it. Meantime, we can read his paper. I found his paper in archive.
Do you hear me?
Yes?
Okay, so sorry for this, probably.
Okay. But your file disappeared.
I will. Okay, give me 1 minute, so I have time. Do you see it?
No.
Not yet.
Oh, yes.
Okay. Okay. So I can repeat. So this is the formula for H2. As I said, the crucial thing was to obtain that H2, which was on the interval from 0.95 to 1, that is x minus 2 beta. And now we obtain a nice identity. This is a very nice identity, which follows directly from the formula for H2. Because if we plug this H2 into this identity, we obtain that to this identity we obtain that it holds. So because if we take H2, so this is H2. So what we have to do here, we have to, this is the formula for H2. So we take now translation by 1/2. So this composition does nothing. We obtain now H2. For H2 will be H1 T1/2 H inverse T1/2, but we have to have T1/2 over here. So this cancels. This cancels. This cancels. This cancels. T1/2 with T1/2 cancels. We get H inverse, and we have H1 inverse. So it cancels. So everything cancels. So this is identity. And now take the following composition: 2 beta H2. If we take 2 beta H2, so we see that H3 of X is equal to X on this interval. Why? Because H2, we remember H2 of X was equal to X minus 2 beta on exactly the same interval. So if we take 2 beta, the composition of this rotation, so we obtain that H3 is equal to 0.951 for this. And now we can write down a new identity. This identity is, again, it's very simple. Why? Because it uses this identity. Why it holds? Because if we take H3, which is 2 beta, so we have here minus 2 beta minus 1/2. Here we have T2 beta H2, and here we have H3 2 beta T2 beta, and here we have T2 beta plus 1/2. So what we obtain finally, this will cancel with this and remains 1/2 or minus 1/2. It doesn't matter because it is modulo 1. H2. Here we H2. Here we have again H2. This will be H2, and here we have T4 beta T1/2. But we see that this formula from the previous identity, this was equal to identity. Therefore, we obtained that this is T4 beta. So we have a nice formula, a nice, for a while we were thinking that we are done in this moment, but we were wrong. Okay, so this is the formula, which is pretty nice. And now will come, I think, that the funnest trick in the whole proof, because this formulas, unfortunately, is not this identity is not satisfactory for us. Why? Because if you compute the number of beta which occurs on the left-hand side and on the right-hand side, you will see that this is the same. Here is 4 beta, and here is also 4 beta. Because this is 0, 2 beta and minus 2 beta, this is 0 beta, but in H3 we have 4 beta, and in H2 we have no beta, but in H1 it was 2 beta and minus 2 beta, so it cancels. So from this follows that on the left hand side and on the right hand side we have 4 beta. So it is not, so this is this condition we have to have, that K is different than K1 plus KL. It's not satisfactory. It's not satisfied here. But here is a nice trick. Look, we take the following function. We take the function f2, which is again some freedom in choosing this function. It must be 2x on the interval from 0, 49. From 0 to 0.49. And if we take the function h4, which is h2 composition with f2 and now taken the inverse of f2, we obtain h4 in the following way. This is h2x of 2x over 2 and x for x from 0 to 1/2, and x from x for x from 1/2 to 1. This is simple. This is the only okay. So what is done here? H3. If we take from on this interval, so we take that this is H3 2x, and again we are in the value of this function is such that inverse to this function is just 1/2. So this is this function. This is in fact on the interval from 0 to 0.49, but we assumed that this function is identity if we are behind this interval. So this will be identity, but this will be again identity. So this is true for all from 0 to 1/2. And here is identity. Okay. Why? Because as I said, close to 1/2, this function H3 is identity. So we'll have 2x over 2x, so will be identity. And here we have x beyond this interval. So we have this function. But if we take the following, and this is last trick, we take the following composition, namely, we take H4, rotation with 1/2, H4 and rotation which 1/2. So we'll see, we take this function, rotate by 1/2, take H4, so we will have identity then, and 1/2. So in this way, we obtain this function okay, so by this trick, we obtain that the graph of this function is built of 2 scaled copies of H3. So this is the whole idea, was to obtain a new function which is built from 2 scaled copies of H3. This is exactly what we did here. Due to the fact that this function is here H2x over 2, and here is identity. So we transform this to 1/2. Here this function is identity 1/2, so it do nothing on the interval from 0 1/2. On the interval 1/2 1, this does nothing. We transform 1/2, so there is the reason why we obtain here 2x minus 1 over 2, and this is transformation rotate by 1/2, so this is plus 1/2. But if we look on this set, on the graph of this function, it is exactly the graph of the function H3, but rescaled. So there are 2 copies of this. So we have some function, say H3. This was some function H3. And what we did, we rescaled this. So we obtained the graph which is composed of 2 such copies of this function h3. But what we know about h3? About h3, we know that it satisfied the following identity: 2 beta plus 1 half, h3, 2 beta minus 2 beta minus 1 half, h3, and it was equal to t4 beta. And since the function h5 we obtained from the function h3 and scaled this x1, we transform on x half, 1 half. In this way, we obtain this h4, h5. So this equation, this identity, we can rewrite in this new coordinates, in the coordinates x half, y half. And how will this equation look like in this new coordinates? Will be t beta plus 1/4. This function h3, but in this new coordinates is just h5. This is minus beta, and this is h5. But fortunately, this is 2 beta. And now, if we compute the number of betas which occur on the left-hand side and on the right-hand side, it will be different. It will be different. Why? Because on the right-hand side, we take 2 beta. It hasn't changed anything here because we have beta and minus beta. In h5, it changed nothing. But why? Because h5 was in h5, to obtain h5 from h3, we do nothing with beta. We take function f2, we take function with this rotation by 1/2, and we do nothing. And therefore, this is exactly in h5 occurs beta as many times as it occurred in h3. But we know that we computed that in h3 it occurred 2 times. So will be on the left hand side, we will have here, we have 4 beta, and here we'll have 2 beta. So in this way, we obtain our exactly the identity we wanted to have. Now I plug all elements in the formula 6, and we check that exactly on the right hand side we have 2 beta, but here we had only on the left hand side we have h beta. So this equation is satisfied. And look, in all these considerations, we don't use that beta as of the particular form. It was enough that beta was sufficiently small. If beta was less than 10 to the power minus 3, all computations went through. And in this way, we obtain this formula. And look that all these functions, G1, GL, were defined on some subintervals. Because we had freedom, we were able to define this function such the way that they are trivial, so on some subinterval. And also regularity of these functions, we had a lot of freedom in defining the regularity. So it could have been smooth, it could have been piecewise-affine, whatever. And this completes the proof of this lemma. This completes the proof of the whole theorem, and the proof of. And this is the end of my talk. I finish with some references to I mentioned about. So this is the paper by Avila, this paper by Calegari, Freedom, John Franks, and Frank's Handel, where this question was asked for the first time, and the original paper by Gromov. And the last paper, this is the paper by Andrzej Navas, where he formulated the list of 33 open questions, and 3 of them are already solved. So this is one I presented now, but 2 other are also solved. So there are only 30 open questions. Okay, so thank you for your attention and for the opportunity to give this talk. Thank you.
Thank you. Any questions, comments? Well, I have a couple of questions. First, I don't know if you mentioned it. So this proof, does it work, for instance, for the Thomson group of piecewise linear homeomorphisms with derivatives equal to powers of 2 and breakpoints equal to dyadic points?
Yeah, I think that it could be. Yeah, yeah, I think that we were thinking about this. It should work. Yeah, it should work also for Thomson group. It doesn't work, and this is open question. And Artur Avila wrote in one of his papers that this is probably so challenging problem that he's is even unable to make any guess about is it true or not. To prove similar result for the groups of analytic homeomorphisms. It doesn't work because, as you see, in all these computations, we made use of these G-tree transformations. If they are equal to identity on some subinterval, they are just identity. So we don't have such freedom in analytic, in the groups of analytic homomorphisms. Therefore, we are unable to extend this. But it is an open question, definitely. But we have some ideas. But I can't say nothing more about this. It is open question to extend these techniques or to prove that rotations are distorted in the group of analytic homeomorphisms.
I see. Thank you. And another question. So you obtained that you have logarithmic growth, at most logarithmic growth on some subsequence of integers. Yeah. But can you say more? Can you prove that it's true on for all integers or disprove it?
Yeah, it could be. Yeah, that's true. But because you see, because the iterates ni alpha. Because what I had to have that ni, the sequence is such that ni alpha is in the interval 0b0. So this sequence is sufficiently dense, yeah, in the set of all the integers. So it's relatively easy. Yeah, that could be extended for all of this.
Is it easy to show?
Sorry.
Yeah, that's right. So is it easy to show that this is a sharp bound that you cannot prove better than logarithmic?
Well, I don't know. I haven't been thinking about this, but probably not. Yeah, probably not. But I have no, I don't know. I can't answer this question.
Okay, thank you. Kostya, you had a question?
Yeah. So I also have one question in this direction. Actually, some of my questions already asked by Artem, but I have one more. So you sort of prove this logarithmic growth, but maybe based on how to sometimes works with this irrational rotations, based on some Diophantine properties of the rotation, you can prove some more some better bound. So maybe can you relate somehow this bound with like Diophantine properties of the continuous fraction of this rotation, and maybe to prove not logarithmic growth but even something like stronger?
Yeah, I think that for some irrational rotations, but if you know something about this rotation, so Diophant or number, or it is possible, but it doesn't follow directly from our proof. So probably we'll have to do this, because at the beginning, because the question was whether there exists such distorted homomorphism in the group, and at the beginning we proved that the rotation with a rotational number square root of 2 minus 1, that these are distorted. It was our first proof, and it was extended, very more complicated, and it was extended to this proof. But I think that if we take some particular rotations, so we will be able to get a stronger bound for the growth of this.
Okay, thank you.
Thank you.
Any other questions, comments? If no questions or further comments, so let's thank again Tomasz for a great talk.
Thank you. Thank you. Thank you very much.
Goodbye.
Bye-bye.
Bye.